Hello, Mr. Aaron, Mr. Ryan. How are you today?
Good.
Okay, you play the Chinese chess, right?
Yeah.
You know the chess in the ball, yeah? The chess. The
People
horse.
won't know Chinese chess because they not Chinese.
Okay. That's
Maybe.
fine. You know the horse, yeah, or the knight in the chess.
Yeah.
Wait. Let me do it. The horse, or horse in Chinese chess, or the knight, yeah. Knight.
What knight? A knight is a soldier.
A soldier on a soldier on a horse.
They don't know.
Wow, horse on a horse. Yeah, a horse. Sorry about my writing. Yeah. Yeah.
Yeah.
It's the knife. Okay.
Yeah. Needs an ear.
Sorry.
It needs an ear.
Okay, let's wait. This is not a drawing lesson. Yeah. Okay. And he got a knife. Yeah. Got a sword.
Soldier.
Yeah. Got a sword. Okay.
Like this.
Yeah. That's what I'm saying. Yeah. You jump always one offset and
It's
two.
entrance
Right?
3.
So how many? Even an unlimited, unbounded chessboard. Yeah, with the grid. Okay. Yeah, and a knight, for example, if it's here, how many ways can it jump? How many ways?
8.
8 way down. Look, it could be here.
Do it.
Yeah, way down. Ryan, look, it could be here, and here, and here, right? Yeah? Am I? Yeah?
Yeah.
Right, are you okay?
Yeah.
You know what I mean? Okay, so given an infinity ball, and if this is 0, right? And I give you the ninth position, saying here, that's RC, right? RC. Here is R, here is C. Yeah, and this is minus. Okay, so it's a axis, and I want you to tell me that the minimum number of moves for it to return to the center, right? Yeah, maybe I can draw a little bit. Do you get it? Yeah?
Oh yeah, I get it.
You get it, yeah? Okay, so for example, let's draw. Okay, so for example, here is 0, 0. Okay, let's do this. Yeah. Okay, wait. Do another one.
It's not equal.
That's okay. So here, this is original position. This is a target. We're target. And if the soldier is here, so how many moves can it jump from to this point?
2.
2? How? How is it 2?
Wait, let me think.
You can try. Yeah?
Wait.
Okay.
Wait.
Yeah?
Wait, let me
Yeah.
get it straight.
Wow.
3.
Yeah, so here, right? 3, yeah?
Yeah.
And how about here?
2.
Way down. Okay, so you get it. So look, if it's unbounded, yeah, unlimited, there is no boundary of the chess. I give you a number, like here. If I give you the answer 1, 0. So 1, 0 is this point. You need to tell me is 3. And 2, 0, you need to tell me is 2.
How's that 2, 0?
Here. Look, if this is 0, 1, 2, and here is 0, 1, 2, axis, right?
Yeah.
You go. Okay. So does it make sense? The rows, columns. Okay. Okay. Do you understand this problem? Yeah, you understand. How can we do this?
Okay, so for example, here as you just said.
Yeah.
Okay.
Yeah.
So you're just gonna work backwards.
How? I mean,
It
have
could
you
be-
got the mind
It
and
could
then
be here and here before.
Okay. Yeah. So any idea how we solving this?
And then
How do we solve this problem? Just any source, random source will be fine. It doesn't have to be correct. Just give me how do you solve this problem? How do you ask computer to solve this problem? Given
proof
location.
forcing.
How do we prove forcing?
Checking
Checking every possible. We're going to what?
possibility.
How do we solve this problem?
Proof forcing.
How do we prove forcing?
Checking every possibility. Infinity.
But it's infinity. How do we prove forcing? I mean, yeah, obviously proof forcing. You can check the next position, right? Obviously they are unlimited here.
Do
You
you
can-
use
look.
the 2 pointers?
No, look. The horse here, and it has A position next, right? Yeah. And from each location, it has another A position, right? Right.
Yeah.
So you could brute force each position until it follows this, right? Right? Alright?
Yeah.
But it takes time, right? Because look, A, the number of possibility for the first step is A. And another second 2 steps, if the knight makes 2 steps, is A times A. Another 3 steps. So A to the n, right? Yeah, to the power m. And if this position is very, very far, and it could never find it, for example, yeah, it could, because you're trying this position and it randomly, you don't know where you want to go, right? The knight don't know where to go, am I right? Yeah? So, and the other thing is that it could repeat. If you jump it here, and the next time you don't want to jump it back, right? You need to remember where you already jumped, right? Alright?
Mm-hmm.
And how can we solve this problem? We can use the what?
Notebook.
Notebook, yeah, the hash chart. Remember the moves we have visited. But the thing is, this board is unlimited, so it doesn't make sense. I mean, it's not feasible to use the search, right? Because you're going to try to remember all the moves, Eric. We have visited, and that's going to be very inefficient, right? Because if R and C, if this initial location is a minion, alright, a minion step far away from the original. So you're just randomly walking in 8 directions. For example, here. You're here, right? Eric, look at me. Don't lie. You need to answer here, right? You're going to expand your search here, and then search here. Yeah, it's going to take time until you find this, right? Right? You can use the breadth first search or depth first search, right? Am I right? Yeah. Breadth first search and depth first search. Am I right, Eric? Yeah. But that's going to take forever. Am I right? Am I right?
Yeah.
Okay, so can we do this mathematically? Eric, stop drawing, Eric. Can we do this in a better way? Any idea? Do you know what I'm talking about? Why this is not okay? This approach is not very efficient. Yeah. If I tell you, okay, Eric. If I tell you, if this board is limited, if like it's 100 times 100, right? You want to place the knight in a board with 100 and 100, and then you tell me what's the minimum number of moves from this position back to the original, to left top left corner, right? Then we can do the breadth search and depth search, am I right?
So
Yeah.
if it's like this far,
Yeah.
we wanna move closer to it.
Yeah. Yes. Exactly. We want to move closer. Okay.
Yeah.
So what I'm saying, like if the search space, I'm saying why this depth search, breadth search doesn't work, because the search space is unlimited. Do you get it?
Yeah.
If the search space is unlimited, these are the search algorithm, Eric. Breadth search, depth search, brute force search, are inefficient. Yeah, because you got the unlimited search space. It's unlimited. How can you search in the unlimited thingy, right? But if I tell you that this board is limited, like 100 times 100.
That's pretty big.
Yeah, I know, maybe 10 times 10 of 100 positions. Yeah, 10 times 10. Yeah. Then you can do this depth first search, breadth first search, because here, you know, you don't need to check here because it's out of boundary, right? Right? Alright, and then you know it's 100 times 100 possible positions, the maximum, and you can do the breadth first search and depth first search, yeah, until you find the path, the shortest path between any point to here. Alright, does it make sense? Okay. So now, yeah, you mentioned a very good point is that we are here. Yeah. If look at the beginning, this position can be negative, yeah, because it's unlimited array. Look, alright, look at this axis. Here's x, here's y, right? Here, it could be negative, yeah. These are the negative space, alright, negative. But if we turn, look, we want to find the position, alright, look, we want to find the closest position here. Is it the same as here, right? You can always mirror it, right? Alright? The distance between this point to this is the same as the distance between here to here, right? It's the mirror, right?
Yeah.
Yeah? We can turn the negative into positive, right? Alright? Because look, the distance between this point to the original is the same as here. Does it make sense?
Yeah.
It's the same, right? You can mirror it. So let's think about the positive cases only. Now we can turn the negative to the positive using which function? The mathematics, what's this function?
Infinity.
What's this function? Remember? What's this function? ABS function, absolute value, yeah? Okay, so look here. If we are here, okay? And we want to move close to that. So how many positions can it, the previous one? Yeah?
From here?
Yeah?
8.
No, yeah, it's 8, but which two positions are closer to this? And yes, exactly. We don't need to check here because it's drifted away, right? Drifted away, and this bit is further away.
You can try that.
No. This is further. It's further. So only these two positions. But we are not sure which way the best, right? Alright? But we can eliminate these two, right? This another 6, right? Because it has bigger distance, right? It's jumping the opposite direction. It's not the thing we want. We want to move closer, right? Yeah. So it should be this way or this way, and that's it. Look, now what we can do is what? Let's say f function, x, y. Then we can say what? It's equals to mean what? F x minus 1, y minus 2. Or f what? F what? X minus 2, y what?
Y minus
What? Come on.
1.
Yeah, minus 1, yeah. 1 is 2, 1 is 2. And what we need to do is plus what? Mean of these two functions plus what? Plus what? From here, if these two positions can know, we already know the distance between this and this. We pick the smallest one, and then we want to jump from how many steps from these two to here. So if we know the distance between the answer to jump from these positions to this, and is this fx minus 1, y minus 2, and here is fx minus 2, y minus 1. So in order to reach this point, we need to plus what? Plus what?
1.
Yeah, that was what I mean. Yeah, good job. Yeah? That makes sense, yeah? Yeah, and this is what? Because we already know this, we don't need to calculate it over and over again. What does this call? Recursion with...
minimization.
And what does it call?
Dynamic programming.
Top down or bottom up?
Top down.
Top down, where down? Okay, now we can
Take
implement it.
14 minutes.
Okay, then what? If it's Eric, the base case is here, right? is here, Eric. If it's 0 and 0, is 0, right? If it's in this position, in this position or here is what? Is 2, right? Here. How do you jump from this to here?
I don't think.
You don't
All
think?
you can do is like go away.
You can go here and then here, right? Remember, it's unlimited ball.
Oh, yeah.
Right? Yeah? Alright? So 2.
Or you can go there.
No? No. How can you go there? Here. Go here and go here, right? Yeah, okay. So that's it. Top-down dynamic programming. Mathematics. Okay, let's write this.
Very quickly.
Alright. Please define wait.
Cash.
Define f, x, y.
On the
Color.
chessboard, they're supposed to be different colors.
Look, if
Black
x
and white.
equals 0 and y equals 0, its origin return what?
Return
what?
0.
Return 0. Okay, then if xy, look at xy is in what? It's all positive, yeah? In what cases? In these cases. Yeah, you can say in these cases. 1, 1, 0, 2,
2, 0.
2, 0. Return what?
2.
Return 2.
Because he's the biggest. Yeah.
Return what? Return 2, yeah? Remember? Right? Then return minimum of fx minus 1, what? Y minus what?
2.
2. And fx minus 2, y,
Plus 1.
huh? Plus 1?
Minus 1.
Minus 1.
Plus
And-
1. Plus
and then-
1.
Plus 1 outside, okay? Yeah, that's it. And forgot one thing.
Cash.
Yeah, because if you're not doing the cash,
It'll be
why that?
exponential.
Yeah, because you the calculating over and over again. It's like remember the Fibonacci number, huh? Eric, look.
This is how you say exponential.
No. Yeah, look. Fibonacci number F3, F4. F4 equals what? F4 equals what? F3 plus F2. And F3 equals what?
F2 and F1. And
F2 what?
is F1 and F0.
Okay, look at F2. F2 here. Yeah? F1 here. If we don't cache it, what happens? This value will be calculated over and over again, right? The same thing here. Because look, fx minus 1, fy minus 2, yeah? Eventually, if you're not caching it, this value will be calculating over and over again, and this will make the time complexity exponential, right? Right? Am I right? But now we're doing this using cache. And at the beginning, if you need to pass this x and y, which is absolute value, right? Alright. If this is a function, we need to call is what? What we need to call is f absolute value of x and absolute value of y, right? Yeah? Alright? And because absolute value, this could go to the minimum, right, Eric? So this needs to absolute value as well, Eric.
Good.
There's one thing here. It's ABS. You need to put this ABS value to all of it. Why is that, Eric? Do you know why we need to do this?
Because like x minus 1, y minus 2, x minus 2, minus 1.
It could be what?
This bit.
Yeah.
Included this.
So what I'm saying is the x minus 1, y minus 2, x minus 2, y minus 1 has to be.
It's like the board. We just pretend there's a board.
Yeah. We need to put the absolute value of it, yeah?
Yeah.
To get what's absolute? Absolute of minus 3 equals what?
3. No, yeah.
Absolute 100 equals what?
100.
Yeah, well, absolute 0 equals what?
0.
Absolute minus 0 equals what?
0.
Yeah, well
There's
done.
no such thing as minus 0.
Yeah, but yeah, okay, you are right. But computer, you can put -0. It's actually the same as 0. Okay, so this is top down.
Not possible.
Okay.
Well,
Okay, so
no,
Eric,
possible.
can you tell everybody in the world what have you learned so far, as short as possible?
Okay, we learned about the
Wow.
chess, and we're gonna play it. Only kidding.
Yes.
Chessboard, and we're gonna do the hats, and gonna do the target.
Yeah.
And we're doing
So what are you trying to solve here? I just want to know what have you learned? What's the
minion of knight moves.
yeah? What's the problem and how are we solving this? Just answer these two questions. What's the problem? What's the problem here? And
you
how
need to do with minion moves.
minimum moves?
Yeah.
Yeah.
Not the greatest.
They're minimal. Yeah, because greatest there's no answer, right? You can always find a bigger move, right? Am I right? Yeah. You can always jump further, right? Am I right? There's no such thing as the maximum number of moves, but there's a minimum number of moves, am I right?
Yeah.
Yeah. Okay. Okay. And how are we solving this?
Dynamic programming.
Yeah.
Top down.
And how are we implementing it?
Memorization.
Recursion with memorization. Remember the cache
We're
thing.
doing top down.
Okay. 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 That's it for today. Good job.